Hello, am I audible?
Yes, sir.
Okay. Any doubt from last class to any one of you?
No, sir.
Okay. So we have to somehow prove this ratio Q2 by Q1 equals to T2 by T1, which we are calculating in last class. So next we can do from this part, let's say for B to C, it is adiabatic process. So at point B, we have pressure P2, volume V2 and temperature T1. And at C, we have pressure P3, volume V3 and temperature T2. Since this particular process is adiabatic, and for adiabatic, I had defined you above equation of state in terms of temperature and volume. It was T V to the power gamma minus 1 equals to constant. So let's say for B, take it as first. So it will be T1 V gamma minus 1 equals to T2 V gamma minus 1. Mamuna, is it clear?
Yes, sir.
Using the relation T V to the power gamma equals to constant. I'm using this part. So we can write T1 divided by T2 equals to V3 divided by V2 whole to the power gamma minus 1, being common from both these two terms. So I've just taken outside from both. So if you move this exponential to other side, like if you have x squared equals to y, so if you move this square to other side, it will become y to the power half, which is also written as root of y. It means exponential on moving to other side from one part to another or during transformation, it may get reciprocal. So if you move this exponential to other side, you will get V3 divided by V2 equals to T1 divided by T2 whole to the power 1 divided by gamma minus 1. Let's say this is equation first. Again, for D to A, at point D, we have volume V4 and temperature T2. So it will be V to the power gamma minus 1, T to the power 1 equals to, at point 1, we have temperature T and volume V to the power gamma minus 1. So from this part, just move T2 to the other side. So you'll get V4 divided by V1 whole to the power gamma minus 1 equals to T1 over T2. Or if you move this exponential to other side, you'll get V4 divided by V1 equals to T1 divided by T2 whole to the power 1 by gamma minus 1. Let's say this is equation 2. Mehreen, is it clear to this part?
Yes, sir.
Safullah, any doubt?
I joined a bit late, sir. Can you explain B to C?
Okay. In last class, we have derived up to this part. That is Q2 over Q1 is equals to this expression. So we have to somehow relate these volume with one another so that this term and this term may get cancelled out. So for B to C, according to the graph of heat engine, at point B, we have pressure P2, volume V2 and temperature T1. At point C, we have pressure P3, volume V3 and temperature T2. So we have to relate volume and temperature, since at this point we have T1, T2, and similarly at this point T1, T2. So at this point, we have volume V2 and temperature T1. So according to this relation, we may write for B, T1 V2 to the power gamma minus 1. And at point C, we have temperature T2, volume V3 to the power gamma minus 1. So on rearranging, I have derived V3 divided by V2 equals to T1 divided by T2 to the power 1 by gamma minus 1. Saifullah, is it clear?
So can you say how you get gamma minus 1?
This relation, just 1 minute. In last class for adiabatic process, let me define you. Just see this. First, we have pressure and volume. PV to the power gamma is equals to constant for adiabatic process. Similarly, if you convert in terms of temperature, it will be TV to the power gamma minus 1. And in terms of pressure, it will be P1 minus gamma T to the power gamma equals to constant. So for adiabatic process, we may have these two different equation of state. So I'm just using this second one. Okay, Saifullah?
Yes.
TV to the power gamma minus 1 equals to constant. So now from equation first and equation second, we have same quantity in right hand side. So on comparing, we can say V3 divided by V2 must equals to V4 divided by V1. Move this V2 to right side and V4 to left side. So you will get V3 divided by V4 equals to V2 divided by V1. I've just shifted this one to this point and this one to this point. By cross multiplication, you can say. Memuna, any doubt?
No, sir.
Okay, just write it down to this. Have you all done?
Yes.
Saifullah, written?
Yes, sir.
Okay. Now, since we had Q2 divided by Q1 equals to T2 divided by T1 multiplied by ln V2 by V1 V4 by V3, I think. V4 by V3 ln V2 by V1. In numerator, we have V4 by V3, but according to this, V3 by V4. So if you rearrange this particular term, or if you reverse this particular fraction, according to the concept of log, it will be defined by ln x to the power minus 1 will be minus of ln x, or it will be further equals to 1 by x. Is it clear? So if you reverse the fraction in log, then there will be negative sign multiplied with its coefficient. So you may write this particular term to be this. Mamuna, is it clear?
Yes, sir.
Now, we may further say this Q2 is being heat ejected out from the system, and Q1 is heat being absorbed to that system. So Q2 will be taken as negative and Q1 will be taken as positive. So this will be negative and this will be positive. So on further, we may write minus of Q2 divided by Q1 equals to T2. If we have to reverse this particular fraction, then there will be negative sign ln V3 divided by V4 whole divided by ln V2 divided by V1. Now we have same quantity in numerator and denominator for log, so they will cancel out. So this quantity and this quantity will cancel out. Minus sign will cancel out. So you're left with Q2 divided by Q1 equals to T2 divided by T1. Mamuna, is it clear?
Yes, sir.
Saifullah, any doubt?
So please explain from the sign part why
Okay.
we take the minus.
In sign convention, I defined in first class for heat, if it is being supplied to the system, we take positive sign. And if it is being ejected out from the system, it will be taken as negative. Since in this part, we have Q2, which is ejected out from the system, so it will be taken as negative, and Q1 supplied to the system, so it will be taken as positive. So using sign convention, I'm taking this. Is it clear?
Yes, sir.
Okay, just write it down. Saifullah, done?
1 minute, sir. Finish, sir.
So efficiency equals to simply work done by heat absorbed, which was further equals to 1 minus Q2 by Q1. And Q2 by Q1 is also equals to T2 by T1. So we can write 1 minus T2 by T1. So this will be generalized relation to find eta or efficiency of this heat engine. Now there will be question, why efficiency of heat engine can never equals to 1? Mamuna, any guess related to this expression? Why eta can never equals to 1?
No, sir.
Okay, just let me define. Let's say this particular eta to be 1. So this T2 must be 0 so that this fraction becomes 0. So this 1 equals to eta. Is it clear?
Yes, sir.
So whether the temperature 0 Kelvin will be possible for any existence of matter or not? You'll say no, at 0 Kelvin, there will be no existence of any matter. So it can't be possible. So for eta to be unity or to be 100%, there should be sink of 0 Kelvin. And for 0 Kelvin, there will be no existence of any matter. Hence, it can't be possible. Is it clear?
Yes, sir.
Saifullah, is it clear? Why efficiency of heat engine can never equals to 1 or 100%?
Yes, sir.
For eta to be 1 or 100%, T2 must equals to 0, and at 0 Kelvin, there will be no existence of matter. Hence, it can't be possible. So eta can never equals to 1. Mehreen, any doubt?
Yes, sir.
Okay, just write it down. Using the above concept, try to find this. Find efficiency of heat engine working between ice point and steam point. Marine, what do you mean by ice point?
Melting point.
Melting point of what? Ice. Okay. So what will be its numerical value? (0°C). So in terms of Kelvin, it will be 273 Kelvin. So we have one of the temperature to be ice point, 273 Kelvin. The other temperature is steam point, that is 100°C, or in terms of Kelvin, it will be 373 Kelvin. So which one is higher temperature? Steam point. So it will be taken as temperature of source, T1, and the lower temperature, 273 Kelvin, temperature of sink. Using these two values, try to find efficiency using the above formula. Okay, Safullah, good. So related to the above formula, you may write eta equals to 1 minus T2 by T1. So 1 minus T2 is 273 divided by T1, 373. So on solving, it will be 373 minus 273, 100 divided by 373. So it will be about 0.27, or in terms of percentage, it will be 27%. Mamuna, is it clear?
Yes, sir.
Abdul Wahid, any doubt? Let me give you another question. A heat engine working between 27 degrees Celsius and 1 to 7 degrees Celsius absorbs 8 kilojoule heat per cycle. Find first efficiency, second work done per cycle, and third heat ejected per cycle. Let me give you some hint related to this part. We have initial temperature 27 degrees Celsius and higher temperature 127 degrees Celsius. So 27 or 127 just convert in terms of Kelvin. So a smaller value will be temperature of sink and higher temperature will be temperature of source. Using these two values, try to find eta. Then it absorbs 8 kilojoule from source. It means it is the value of Q1. So related to the above formula of efficiency in terms of heat, you may write eta equals to work by heat absorbed. You'll get work done, and then work done is also equals to Q1 minus Q2. You'll get the value of Q2. Try to find using this. In problem while solving, Saifullah, any problem?
No, sir.
Okay. Okay, Saifullah, let me check. We have lower temperature 27. So T2 will be 273 plus 27, that will be 300 Kelvin. T1 127 plus 273, so it will be 400 Kelvin. So eta equals to 1 minus T2 by T1. So T1 is 400 and T2 is thus, so 400 minus 300, it will be 100. Divide by 400, 1 by 4, that will be 0.25. So it will be the first answer. Mehreen, is it clear?
Yes, sir.
Second part, work done per cycle. So using eta equals to work done by heat absorbed. We have heat absorbed 8,000 joule. So work done will be eta, that is 0.25 multiplied by Q1, 8 into 10 to the power 3. 25 into 8, 200. So it will be just 2,000 joule or 2 kilojoule. And third is work done equals to Q1 minus Q2. So work done is 2000 and Q1 is 8000. So Q2 will be equals to 6000 joule or 6 into 10 to the power 3 joule. Mamuna, is it clear?
Yes, sir.
Mehreen, done?
Yes, sir.
Okay. Mamuna, done?
Yes, sir, finished.
Matthew, you may take a screenshot from which we have started. From this part.
Okay, sir.
Done?
Yeah. Yes, sir. I took a screenshot of this. Yeah. Yes, sir. Got it.
Okay. Now there will be, what do you mean by Carnot engine? So you'll say Carnot engine is also a heat engine, which having maximum efficiency. We just assume to be this engine to be ideal. So it is also a heat engine. So there will be a question either in terms of heat engine or directly in terms of Carnot engine. So then don't get confused about these two terms. It is also a heat engine. So there will be a question on what condition efficiency of heat engine will be maximum. So you'll say if two heat engine, one is a reversible process working and the other is irreversible process working. If working between same source and same sink, reversible heat engine will have always greater efficiency as compared to irreversible heat engine. So a heat engine working between same source and sink will have greater efficiency and reversible process as compared to irreversible process. It means we can say heat engine, which is in reversible process, will have always greater efficiency as compared to irreversible process. And next, there will be no heat engine possible whose efficiency will be greater than unity or equals to unity, which I had defined above. Okay, so you may write this. You all have done?
Yes, sir.
Okay. Now, there will be limitation of first law.
1 minute, sir.
Okay.
Yes, sir.
Definitely. Okay. So next is there will be some limitation of first law. First law simply defines the flow of heat that to be unidirectional, that it always flows from higher temperature body to lower temperature body, and reverse can't be possible. So it's defined unidirectional flow of heat, that is from higher temperature body to lower temperature body. And reverse is not possible. And reverse is not possible. Mamuna, any doubt?
No, sir.
So this leads to the basis of or origin of second law or second law of thermodynamics. Anyone who know about it? Second law of thermodynamics. Namuna, any idea?
Um, in second law of thermodynamics, I think there are two statements. One is the
Yeah.
Kelvin.
And one
Yeah.
is the clauses. Okay.
Yeah.
So can you state any one of them?
Yes, sir. The Kelvin is that no process is possible whose sole result is the absorption of heat from a reservoir and complete conversion of heat into work.
Okay.
And the clauses one, that there is no possible which is possible whose sole result is the transfer of heat from a colder object to a hotter object.
Okay. In general, for second law, just remember, it states there will be no possibility of transfer of heat from lower temperature body to higher temperature body unless or until some work is done to do this particular process. Let me define you by giving an example. Suppose if you have to lift any object from ground surface to some higher surface. So at ground level, there will be lower gravitational potential energy. At some higher level, it will have some higher gravitational potential energy. So if you have to move any object from lower gravitational potential energy to some high gravitational potential energy, you must have to apply some external work done. It will be not possible to go that object from lower point to higher point by themselves. Similarly, in case of flow of heat, we can say there will be no flow of heat from lower temperature body to higher temperature body unless some work is done to do this particular process, which is the result or main conclusion part of this Kelvin and Clausius experiment. So we can say no flow of heat will be from lower temperature body to higher until external work is done. Now, on the basis of this particular law, we define two different engine, which is called, or machine, which is called a refrigerator. And the next is heat pump, which may work just opposite of heat engine. Let me define you. First, write it down till this. Saifullah, done?
Yes, sir.
Suppose in case of refrigerator, one of the compartment, this is working tool, and another compartment. The first one is called cabin, and the second one is called surrounding. So it extracts heat energy from this cabin at lower temperature Q2, at some temperature T2, and do some work on it from any external agency, in this case by compressor, so that these two combines to form Q1 to eject out more amount of heat into surrounding at some higher temperature. So the working of refrigerator is it extracts heat from any cabin to cool it down and do some work from any external agency, that is compressor, to eject large amount of heat into surrounding, which is sufficiently at larger temperature as compared to cabin. So it is doing, or it is just doing work to flow heat from lower temperature body to higher temperature body. Is it clear? Namuna?
Yes, sir.
Similarly, in case of heat pump, this is one cabin, this is another. So again, in this part, it absorbs heat from low temperature. So this, in this case, it will be surrounding. Some work is done by compressor W, so that it will become Q1 to eject into room, that is a region of interest in with this part, to warm it. So refrigerator or working of refrigerator is extract heat to cool down this cabin or region of interest, or heat pump is eject heat into room to warm it. But both work in the same manner and in between same source and sink. Is it clear?
Yes, sir.
Saifullah, any doubt?
No, sir.
So let me define for the refrigerator. It extracts heat from cabin. In this case, it is region of interest. To cool it down by adding work from compressor it ejects Q1 into surrounding. So we can define its working performance. Alpha equals to, in this part, how much energy we are giving to this particular system. So you'll say work done in the form of electrical energy, and how much work is doing by this refrigerator. So it is the amount of ejection of heat from that cabin to cool it down. So working performance is heat extracted from cabin divided by work done. So it will be equals to alpha equals to heat extracted Q2, work done is W, which is equals to Q2 divided by Q1 minus Q2, or should be also equals to T2 divided by T1 minus T2. Mehreen, is it clear?
Yes, sir.
Okay, just write it down. You all have done?
Yes, sir.
Saifullah, done?
1 minute, sir. Yes, sir.
For heat pump, we can say it absorbs heat from surrounding at low temperature by adding work from compressor. It ejects large amount of heat into a room that is a region of interest to warm it. So in this part, if you want to calculate working performance, so beta will be for heat pump, amount of energy given to this particular system is work done in form of electricity or by compressor. Amount of energy that is given output of this particular system is Q1. So it will be heat ejected into room, that is the output part, divided by input work done. So it will be Q1 divided by Q1 minus Q2. In terms of temperature, it will be T1 by T1 minus T2. Now let me define a relationship between all these three different terms. Let's say heat engine, efficiency of heat engine, working performance of refrigerator, and this heat pump. Beta equals to 1 plus alpha, which is equals to 1 by eta. Just remember this relation. Just write it down. You all have done?
Yes.
Saifullah, done?
Yes, sir.
Let me define you those two statements related to this law as well. Kelvin process. Let's say this is source or at high temperature, lower temperature. So heat is being absorbed from it and its sole process to convert into work done. It won't be possible. Next, if this is at lower temperature, sink or any lower temperature body, and this is at any higher temperature body. So no process possible. Whole sole result is to convert or transfer heat from lower body to higher body. So you'll be asked these two statements as well. So let me define. In first part, you can say, no process is possible whose sole result is absorption of heat from source and conversion into work. In second part, you can say, no process is possible whose sole result is transfer of heat from lower temperature body to higher. Saifullah, any doubt?
Sir, in Kelvin, heat won't be transferred to sink.
No. There will be no possibility of any process in which absorbed heat directly converted into work done without any loss of energy into sink. If this will be possible, its efficiency will become 1. I had proved you above, efficiency of any heat engine can't be possible to equals to 1. Okay?
Yes, sir.
Just write it down. You all have done?
No, sir, wait. Done, sir.
Mehreen, done?
Yes, sir.
Okay. There will be a question related to this refrigerator or heat pump. In a closed room, if door of fridge is kept open, what will happen to temperature of surrounding? Will it increase or decrease? Let me define you this process. Suppose this is any closed room in which there is a fridge whose door is kept open like this. So what will happen if its door is kept open? So you'll say this cabin and this entire room becomes common body. So it absorbs Q1 amount of heat, Q2 amount of heat at lower temperature from cabin or from its whole surrounding. By adding some amount of work from compressor, it ejects Q1 sufficiently higher amount of energy into same surrounding. So on each cycle, the amount of work supplied by compressor, which keeps on warming this particular room, hence temperature of room will get increases. Is it clear?
Yes.
Saifullah, any doubt?
So please repeat it again.
if you kept this particular door to be open of this particular fridge, so this cabin and this entire room becomes common system. So if it has to absorb Q2 amount of heat from this cabin, now since it is open to the surrounding, so it may absorb Q2 amount of heat from the surrounding, which is at lower temperature. So it will have some smaller value Q2. By adding work from compressor, this fridge ejects out Q1 amount of heat into same surrounding. So for each cycle, it keeps on adding amount of work by compressor to this particular surrounding, which will be responsible to increase its temperature. Hence, temperature of this particular room would increase after some time. Saifullah, is it clear now?
Yes, sir.
Let me define you by using number. Suppose it has to absorb energy from the surrounding and is absorbing just 8 joule of energy. It has to do some work by compressor. So let's say it has done 2 joule of work by compressor. So Q1 now becomes 10 joule. So for each cycle, you'll say how much energy is supplied to this particular system. Q1 minus Q2, that will be 2 joule. So this 2 joule heat will leads to increased temperature of this particular room. Hence, temperature of room increases in this condition. Matthew, is it clear?
Yes, sir.
So you can say if door of fridge is kept open, so cabin and whole room becomes same. So it absorbs lesser amount of heat from surrounding by adding work from compressor it ejects larger amount of heat into same surrounding. Hence, temperature of room increases. Marine, in and out. Abdul Wahid, any doubt? Saifullah, done?
Yes, sir.
Okay. So this is all about this entire